All right, is this fine? All of you can read it? Decent size, or shall I increase the size? Fine? Okay, very good. So let's look at the governing equations. So the governing equations are nothing but mathematical statements, right? Governing equations for fluid flow and heat transfer, right? Fluid flow and heat transfer. So these are nothing but the mathematical statements of conservation laws, right, of physics, okay? So these are the mathematical statements of conservation laws of physics, okay? What are the conservation laws that we know, which are relevant here? Mass, okay. Conservation of mass is conserved, right? Okay. Okay, and then the conservation of momentum, right? Which is what? Which is what? Which is the Newton's second law of motion. Okay, so that is Newton's second law, which says that the rate of change of momentum, okay, of a what? Fluid particle, right, that we are following, of a fluid particle equals what? The sum of the forces, right? This is the resultant of the forces, sum of the forces acting on it, right? Acting on the fluid particle. Okay, so that is Newton's second law of motion. What else? Conservation of energy. Okay, so that is conservation of energy, that reads as the rate of change of energy, right, of a fluid particle equals what? Equals the rate of heat added, right? Okay, equals the rate of heat added and the net rate of work done, right, by the fluid particle, okay, work done by the fluid particle. So this is conservation of energy, which is also is a law of thermodynamics, right? Which law of thermodynamics is this? First law, okay, this is the first law of thermodynamics. Okay, point. Okay, all right. Okay, so we have these three conservation laws, which are kind of relevant for what we kind of do. Okay, so we'll be writing them in mathematical statements, and we'll discretize them, and then solve them and obtain what we need. Okay, all right. So we will be regarding the fluid, okay, as a continuum. Now, what is a continuum? For the kind of length scales we are looking at, right, for the kind of problems we are looking at, which are all greater than, let's say, 1 micrometer, okay, for all these length scales of the problem, right, we say that the fluid that we have can be treated as a continuous field, right, by disregarding the molecular structure and the molecular motions of the fluid. Okay, so essentially the fluid is composed of some molecules, right? So we are kind of disregarding the molecular structure and the molecular motions, right? Of the fluid, such that we can consider this as a continuous substance, right? Without any voids that are present within the molecules, right? Between the atoms and things like that, so that we can kind of treat it as a continuous substance, okay? So that is a continuum. Now again, this length scale approximation has to be kind of remembered all the time, right? So we are not looking at something that is very small. We are not looking at something that is very small where the properties could be affected by the number of molecules that are moving in and out of the fluid element that we have considered, okay? So, but we are still looking at something that is very small such that, right, or something that is very large such that where the number of molecules that are there kind of represent the particular property for that fluid element, okay? So when you invoke the continuum assumption, you can kind of characterize a fluid or describe a fluid in terms of its properties, right? Okay. So what are the properties for a fluid? You can describe a fluid in terms of its density, okay? Density or pressure, right? You have a pressure is a, and then you have a velocity vector, right? The fluid flow velocity vector describes the fluid, or temperature and so on, right? All these properties are continuously varying across the fluid domain that we have considered, okay, without any voids in the domain, okay. Now, all right, so okay, so but these are also could be functions of both space and time, right? So each of these properties that we have are functions of space, such that is rho is a function of x, y, z, t. Similarly, the velocity vector u is a function of x, y, z, t, and so on, right? So these are all functions of both space and time. Now the fluid element that we consider here, let's say I consider a fluid element like this, okay? So this is an infinitesimal fluid element. So we have x-axis, y-axis, and z-axis. So when we say x, y, z, we are looking at the centroid of this fluid element, okay? Now this is an infinitesimal fluid element with dimensions delta x, delta y, and delta z in all the three directions, okay? Now this is very small, or an infinitesimal fluid element. However, the number of molecules that are there in this are still, okay, these are, let's say these are all the molecules that we have in the fluid element. So the number of molecules that are there inside are quite large in number, right? Such that if we have some molecules going out or some molecules coming in, they are not affecting the fluid properties of this fluid element or particle that we have considered. Okay, so that is kind of good to know. Now, but this fluid element is small enough such that the properties of this fluid at on the faces, for example, on this face, let's say this is, we call it as a east face, okay, or we call this as a west face, right? On the faces, we can obtain the properties using just the first two terms of the Taylor series expansion. That is because the fluid element is quite small, okay? So just by using the first two terms, okay, of Taylor series, we can obtain the properties on the faces. So for that matter, we can denote, let's say, the faces as east and west in the x direction. We could call this as a north face and this as a south face, okay? And similarly, we can call the other faces, which are, let's say, the front face, okay? So this is a front face, and the one at the back as a back face, okay? So we could call east, west, north, south, front, and back, about 6 faces. All right. Now, so if we want to construct the properties, let's say we want to construct pressure on the east face, okay, we could write it as P, right? This is P at XYZ that we have. On the east face is at a distance delta x by 2, right? So I could obtain using Taylor series as P plus partial P partial x delta x by 2, right? Plus I don't need the higher order terms because the element is so small that this is accurate enough to represent the face value of the pressure. Similarly, I can construct what is the value of the pressure on the west face by using P minus partial P partial x times delta x by 2, right? Plus minus and so on, right? So these kind of give us the values on the different faces. Similarly, we can construct it on the north face, south face, front and back and so on. All right. Look at conservation of mass, okay. So conservation of mass, we are looking at again a fluid element, okay, something that we just drew above. What will be a statement of conservation of mass? We say that if we have a fluid element, something like this, okay, we have XYZ. So this is a fluid element. All right, so the conservation of mass, a mathematical statement is the rate of increase of mass within this fluid element should be balanced by the net rate of mass that is entering through the phases. Okay, so if I were to write it, so this is basically rate of increase of mass in a fluid element, right, is balanced by the net flow rate of mass into the fluid element through the phases, right? All right. So what will be a rate of increase of mass in a fluid element? How do we write it mathematically? We have a rate of increase, so we invoke the partial derivative with respect to time, right? What will be the mass of this fluid element? So let's say this is delta x, delta y, and delta z, and the density at the centroid, which could be taken as uniform representation for the entire thing, or the density in the fluid element, right? Now, what will be the mass of this fluid element? That will be the density times the volume, right? So essentially, we have the density rho, and the volume is delta x, delta y, delta z, right? So this is the term on the left-hand side that we have, partial t times rho times delta x, delta y, delta z. Okay. Now we have to look at what is the net mass flow rate, right? The net flow of mass into the fluid element through the phases. What will be a mass flow rate across a particular phase? What will be an expression for mass flow rate in terms of, let's say, the density, right, and the velocity of the fluid and the area of the surface that we are looking at? The mass flow rate would be essentially density, right, times the cross-sectional area times the velocity component that is normal to the surface that we are considering, right? Because whatever is not normal would not enter the fluid element, right? So essentially, so that means rho times, right, rho times we have the cross-sectional area. I would like to write it as AN, that is the normal cross-sectional area, right, times what do we have? Times the velocity that is normal to the surface, right? So essentially that is Vn, right? Some kind of velocity. Now if you are to write this thing, this is essentially nothing but rho times V bar dot An bar, right? That is in terms of a vector notation. Okay. So density times the velocity times the cross-section area. Now what will be the density on this So that means I can write this as the cross-sectional area, that is AN, right, which is any of these cross-sectional areas that we have, times rho times the V bar, that is rho U would give me the momentum, right, coming into the phase, right. So what would be the rho V bar dot AN? So what will be the, if the momentum at the center is rho U, right, that is in terms of x, y, z, what will be the momentum on the west phase? I can use the Taylor series expansion and construct it again. So this would be rho U minus partial x times rho U times delta x by 2, right? That's what we have. Similarly, momentum on the east phase would be rho U plus partial x rho U times delta x by 2, right? That's what we have on the east phase. So this is on the east phase, this is on the west phase. Okay. Now, so we are looking at this second term. Essentially, we're calculating what is this net flow rate of mass into the fluid element. So the fluid into the fluid element, through all the 6 phases, we can have mass that is coming in and out, right? For example, through the west phase, we have mass that is entering. Through the east phase, we have mass that is leaving. Similarly, through the, let's say, north phase, the mass is kind of leaving. And through the south phase, we have mass entering. Similarly, through the back phase and the front phases, we have mass that is entering and leaving. So we have to consider all of these sum to evaluate this second term here on the right hand side. Okay, so that's what we do now. Okay, so then what will be the mass flow rate into the fluid element? What will be the mass flow rate? So whatever is flowing in, we call it, we represent it with positive, right? So from the west phase, we have rho U minus partial x rho U times delta x by 2, right? So this is the density times the velocity. What will be the cross-sectional area for the west phase? Delta y delta z, right? So that would be the cross-section area, right? So that is your delta y delta z, that is this area, right? This times this, okay? All right. And what about the mass that is leaving through the east phase? That will be with a minus, right? So then you have rho U plus partial x rho U times delta x by 2 times delta y delta z, right? That will be the same thing we have. Is that all? No, we have all the 6 phases, so we have to add plus. What will be the mass flow rate coming through the, entering through the north phase? Oh, sorry, entering to the south phase. So we have to consider the velocity that is normal to the surface. Normal to the surface, the velocity component is v, right? And then v is represented here. So it will be rho v minus partial y. I'm coming in the y direction. So that would be rho v minus partial y, rho v times delta y by 2, right? Times what would be the cross-sectional area? Delta x, delta z, right? So that is essentially this cross-section area that we have, that is this guy, right? So delta x, delta z, right, minus we have the mass flow rate that is leaving through the top surface is rho v plus partial y, rho v delta y by 2 times delta x delta z. Similarly, if I extend it to the back phase and the front phase, on the back phase we have rho w minus partial z, rho w delta z by 2 times what would be the cross-sectional area? Delta x delta y, right, minus we have rho w plus partial z, rho w times delta z by 2 times delta x delta y, right? So that's all. So this is the mass flow rate that is there on the right hand side. Now, what do you see? Of course, you see that we have a rho u times delta x delta y delta z, right, times delta y delta z here, and rho minus rho u times delta y delta z here, right? So these terms get cancelled, right? And then we have these terms, this guy and this guy are one and the same, and they represent 2 halves, right? So this is delta x by 2, this is delta x by 2 times we have the same thing. So these two halves sum to 1, right? And then we have three such terms, one here and one here. So we just have to kind of write it as minus partial. We can write it as minus partial x of rho u times delta x, delta y, delta z, and then plus minus partial y rho v times delta x, delta y, delta z, minus we have partial z rho w times delta x, delta y, delta z, right? So we have these three terms on the right hand side, and on the left hand side we had partial t of rho times delta x, delta y, delta z, that is the net rate of increase of mass within the control volume. Now this is an equals here, right? I would send this guy to the left hand side, right? And also get rid of the, assuming that the fluid element is not changing its size, right? So I can get this with time, I can get this out, and then we can get this, cancel these two terms. So what we end up here is, partial rho partial t plus partial x rho u plus partial y rho v plus partial z rho w equals 0, right? So that is the conservation of mass. In a shorthand notation, we can write it as partial rho partial t plus nabla del dot rho u bar equals 0, where del bar is partial x I hat, j hat partial y, k hat partial z, and your u bar is I hat u plus j hat v plus k hat w, right? So we can write this. So this is nothing but your conservation of mass for a compressible, right? The unsteady conservation of mass for a compressible fluid. Okay. Now let's say we have an incompressible fluid, which is where the density is what? Is a constant. Okay, if we have density is a constant, then the first term drops out, right? Then this drops out. Then rho can be taken out of the divergence because density is constant. So then all you end up is del bar nabla dot u bar equals 0, right? So this is your for an incompressible fluid. This is conservation of mass. That is also known as the what? Continuity equation. Why is it called continuity equation? Because it defines the continuity of the velocity field, right? You're taking the divergence of u bar and the continuity is being defined here, right? It has to be a continuous field such that it would be del dot u bar equal to 0, right? That's why it's a continuity equation. So this is in a short form, and if you were to take it in a long form, this would be partial u by partial x plus partial v by partial y, partial w by partial z equal to 0, right? So this is your continuity equation in long form, right? All right, then I'm going to kind of stop here. Okay, thank you.